Welcome to Professional Cipher. This is our first video in Fast API series. In the introduction video, we saw that why should we use Fast API and what were its advantages. So without wasting much time, let's start the video. Before we start a video, remember, we should always create a new Conda environment for any new project. It's always a good practice, plus we have to make something known as requirements.txt, which is necessary when we want to deploy our applications over internet. And we'll see it when we deploy it on Heroku in our upcoming video. So the command for making new environment is conda create -my-env with Python is equal to 3.6, where my-env is your environment name and on which Python version you want to work with. So it makes sure that you can work with multiple Python versions on the same system. We can do this by going into our Anaconda terminal and then by typing this command. Once it is created, you have to just activate it, and that's it. If any package is not installed, make sure you installed it. Now let's see what is our problem statement. So the dataset is originally from the National Institute of Diabetes and Digestive and Kidney Disease. And our work is to build a machine learning model to accurately predict whether or not the patient have diabetes or not. So a background for it, diabetes is a disease that occurs when our blood glucose, also called as blood sugar, is too high. Some of the symptoms shown are increased urination, excessive thirst, blurred vision, increased hunger, and fatigue. So diabetes increases chances of cardiovascular problems, including coronary artery disease with chest pain, heart attack, stroke, and narrowing arteries. If you have diabetes, you are more likely to have heart disease or stroke. So let's see what are the features in our dataset. So the first feature is pregnancy. So it is nothing but number of times a woman is pregnant. A glucose level of the body, blood pressure in millimeters per Hg, skin thickness, that is tricep skin in the fold thickness, then insulin, then BMI, that is nothing but body mass index, diabetes pedigree function. As per this survey, it utilizes information from a person's family history to predict how diabetes will affect that individual. Then the next feature is age, and then comes the outcome, that is nothing but our target variables. Now let's dive into the code. Now first and foremost, we have to import all the required libraries. So I'll be importing pandas as PD, which is nothing but its aliases. Then NumPy for numerical Python. Why we import pandas is to work with datasets. So I'll be importing matplotlib for plotting graphs, and Seaborn works the similar way. So basically both Seaborn and matplotlib is used to visualize our data. So here I'll be reading my dataset, which is there in the root directory. Now as we can see, there are 768 rows and 9 features in the dataset. Now if we see the head of the dataset, we'll get this in return. So dataset info shows that there are no null values in the dataset, and there are no categorical values also there in dataset. Now if we see if there are any null, just to cross check, there are no null values. But there is some issue which we'll see in later part of this video. Moving on towards correlation, we can say that there is no strong correlation between the features. Most of the features don't follow any specific trend. Now if you see the basic statistic of the dataset, there are some features having minimum value from 0, which is not true because blood pressure can never be 0. So we'll do something, we'll convert this 0 into its median value. But we'll not use mean because if there are outliers, it may affect the values. So we'll use median for this. Now we'll see the histogram for each feature. As you can see, this is right skewed, This is I somewhat normally distributed. This is again a right skewed. So as you can see, the most of my features are right skewed. Now we'll see the kernel density plot of each feature. Kernel density plot is nothing but my probability density function. That is nothing that, but my how my data is distributed. As you can see, there are people having diabetes having more glucose. As you can see, one is for having diabetic and they have more glucose. So now we'll move on to pair plot. So pair plot is nothing but it helps to find the relationship between each variables. If now we saw that there is no strong correlation, as we can see there is no strong correlation between each feature, right? Now we want to see that if our data set is balanced or not. So as we can see, it is not balanced, and we have to perform some upsampling later. Now, when we see a line plot between age and insulin, we can see that having diabetes tend to have more insulin level. Here, the yellow line indicates the people having diabetes, and the shaded region here is nothing but the confidence interval of that point. Similarly, if we see a line plot between age and BMI for diabetic people, we can see that diabetic people tend to have more BMI, so it is very necessary to stay fit. And now we'll see the outliers. As you can see, there are some outliers in our data set. And there are generally two ways of tackling this problem. The first way is to remove outliers statistically using techniques like IQR, that is nothing but interquartile range, when data is skewed, or considering data within 3 standard deviations from the mean when data is normally a Gaussian distributed. The second way is to make a robust model which is not sensitive to outliers. This would be our approach, and we'll be using random forest classifier for this. And now it's finally time to make a model. For this, I'll be importing libraries like pandas, numpy. Then I'll be importing Smotomake for upsampling. So SMOT is an acronym for Synthetic Minority Oversampling Technique. As the name suggests, it is something related to oversampling. So we'll see in the later part of the video. So from sklearn.model selection, I'll be importing train test split. What it does is basically divides the data for training and testing purpose. From the same, I'll be importing cross-val score, which gives accuracy of a model. Then I'll be importing the randomized search CV for hyperparameter tuning the model, which is there in model selection only. Then, as I discussed before, I'll be importing random forest classifier for a model. Now to test how a model performs, we'll be importing metrics like confusion matrix and classification report. Then I'll import pickle for serialization, which we'll talk in the later part of the video. Then I'll import warnings to ignore all the warnings that occur while writing a code. Then what I do first is execute it, and then I have to read the data set. So for that there is function read CSV in pandas. So I'll just execute it and store the data frame in the dataset variable. Now to do upsampling, what we do is divide our data into dependent and independent feature. As you can see, for X I have 768 rows and 8 columns, and for Y, that is nothing but my dependent feature, have 768 rows. And now if you see the count of our target feature, we can see that there are only 268 records for the class 1, and there are 500 records for class 0. As you can see, there is some sort of imbalance in the data set. Only 39% of data is for class 1 and rest is all for class 0. What it creates is some sort of imbalance in the data set. For this, we'll be using random forest classifier, and the base model for that is decision tree. And we know that decision tree has low bias and high variance, and it is a condition of overfitting. And imbalanced data set can be one of the reason for the overfitting condition. So overfitting condition can lead to wrong predictions. So what we do is something known as upsampling. So there are generally two ways of handling imbalanced data set. So if you do downsampling on small data set, what it does is loses the trends in our data set. But if you have millions of records and if we do downsampling, there's not much difference in that because we have millions of records. So for doing upsampling, we'll be using Moto Mech as I discussed before. What it does is this library is used to do upsampling, and here I'll be instantiating the object of that class. The fit underscore resample method, what it does is do the work of upsampling, and I'll just execute it. Now if we see the feature, the first it was 768 rows. Now if we see the count have increased, the dimension of our data have increased. And if we try to see our target feature with respect to the classes, we can see that now our data set is balanced, and now we can create a model. Now for making a model, what I have to do is divide our data for training and testing purpose. I've given the test size as 25%. Usually we do a split of 70-30 split, where 70 is for training and 30 is for testing. Or we can even do a 80-20 split. You can give any random state value you want, and let's check its shape. As we can see that we have got 714 rows and 8 columns for independent feature, and for dependent feature we have got 714 rows. Now as we knew, there were some zeros in specific columns which were invalid, and will replace all those with the median values. And now I'll make an object of that model, which is nothing but my random forest classifier, as this is a classification task, and fit the training data for the same. Now how cross-val score works is it checks and gives the accuracy for different folds in our dataset by taking estimator data you want to perform your folds on and CV. So how cross-validation works is, suppose I have data set of 1000 data points. N is equal to 1000. Okay. Now I've given my CV as 10. If I divide 1000 by the CV, which is nothing but my 10, we get 100. Now our model will perform testing on this 100, and training will be done on 1000 minus 100, which is 900. So in my first cross validation, which is my first fold, the first 100 will be for testing, and rest 900 will be for training. In the second fold, what it does is uses this 100 for testing, and rest are for training, and it goes on similar way. So here I'll be getting 10 different scores. If I just execute it, if you see the score now, as you can see, the shape of score, let's see. As we can see, we are getting 10 different scores. If we check the mean of the scores, we got around 82.6, which is nothing but my training accuracy of my model. Now similarly, what we'll do is check our cross validation score for a test data set. And now let's check the average for the same. As we can see, we are getting around 82.73% of accuracy. Now let's see what is the maximum accuracy that we can get from the model, and let's also see the minimum accuracy that we can get from a model. So the maximum accuracy that a model can give is 96%, and minimum accuracy we can expect from a model is around 75%. Now before checking the confusion matrix, let's see how it works. Okay. If you have two classes in a target feature, we get 2 by 2 matrix. I'll just draw 2 by 2 matrix. So above here it is nothing but actual, and here it is predicted. As we saw that there were only two classes, that is 1 and 0, and similarly the model will predict also 1 and 0. Now listen this carefully. If a model is predicting 1 and actually it is 1, so it is what is a model predicting? Positive. Okay, and what is it? True. So this becomes true positive. Now similarly, if we check this value, what is a model predicting? 0, which is negative. And what is it? 0, which is true, so it becomes true negative. Now if we check here, what is a model predicting? It is predicting positive. But what is it actually? It is false. And we do the same. What is our model predicting? It is predicting negative. What is it actually? False. So it becomes false negative. So in the statistic term, this is my type 1 error. Type 1. And this is my type 2 error. In this way, we can read a confusion matrix. Okay. Now let's execute this and check the confusion matrix for the same. As you can see that we are getting true positives 99 and true negatives as also 99, and similarly we are getting false negative also 20 and false positive also 20. Now let's check the classification report. Now to read the classification report, let's see how a precision and recall works. So what precision says is, out of all positives, how much were them actually true? So here we can see these are my positives. See, this all are my positives. Okay, and which were actually true? So this are my actually true. Okay, so I'll write here true positive upon true positive plus false positive. If we check how a precision works, let's calculate the same. So here we can see that what were my true positive? It is nothing but this is the score of 99 divided by 99, because see, it is true positive plus false positive. 99 plus 20. I'll surround this by brackets. As you can see, we are getting around 83.19, which is same as my precision for zeros and ones. And how does recall works is, out of all the positive classes, how much we predicted correctly. So out of all the positive classes, actual positive classes, how much we corrected correctly. So it's a ratio of true positive upon true positive plus false negative. Now let's do this with the help of calculator. Now here, what were our true positive? It is 99 divided by true positive plus false negatives. By 299 plus 20. As you can see, we are getting the same as 0.83. FN score helps us to measure recall and precision at the same time. Basically, it is nothing but harmonic mean of my precision and recall. I hope you have understood how to read a confusion matrix and terms related to it. Now let's move on to hyperparameter tuning. Now what is hyperparameter tuning? In machine learning, hyperparameter optimization or tuning is the problem of choosing a set of optimal hyperparameters for learning algorithm. A hyperparameter is a parameter whose value is used to control the learning process. Hyperparameter tuning is crucial as they control the overall behavior of machine learning model. Every machine learning models will have a different hyperparameters that can be set, and let's see. Now we'll be using random forest classifier for this. Now we see the parameters that random forest takes by pressing shift tab. We can see there are multiple parameters like n estimators is equal to 100. This is nothing but my decision trees. So it uses 100 decision trees by default. Criterion is equal to Guinea by default. As you can see, there are multiple parameters that we can set. Now what we are going to do is play with these parameters. So as you can see, first is we are assigning n estimators as any values between 200 to 2000 and we'll take 10 such values. And if we see max features, it is auto by default. And if we see what all parameters can it take, as you can see, it can take auto, square root and log, and we'll pass those in a variable. Similarly, we'll do for max depth, min sample split, min sample leaf. So guys, remember, while giving it to randomized search CV, we have to give it in key value pairs, where key is nothing but my parameters and value is nothing but my this all parameters that we have decided. Now let's see the random grid. As you can see, our random grid is ready with all these parameters. Now what I'll do is instantiate an object for randomized search CV with estimator as random forest, which we had already created, with random grid with all these parameters, and CV is equal to 10 as we saw what CV does, and verbose I'll give it as 2. Njobs is equal to -1, what it makes sure that it uses all cores of your CPU, so it becomes computationally faster. Now I'll fit. It generally takes time depending upon your CPU. Now once it is executed, what randomized search CV do is take random values. Like suppose it's taking 200 estimators, then it's taking max feature as log 2, then some value from here. It takes random values and gives us the accuracy. That's why the name is randomized search CV. Okay, now let's see what were the best parameters for the same. Now as you can see, the n estimators went up to 1600 with max feature as log 2 and criterion became entropy. So generally by default it is Guinea, but it have become entropy. Now let's see and predict on our test data. So as you can see, our model have decreased false negative values, and let's see the classification report for the same. As you can see, there is bit increase in our precision and also recall. Now let's see the ROC curve for our test data. The AUC for this model was 0.90. If you have multiple models, we can check the AUC value. The maximum, the better. Okay, we have done till here. But now we have to expose our model to our backend. How will we do it? So for this, there is a method called as serialization. What it makes sure that your object is converted into a file. So that's what I'm doing here. See, I'll open a file named as model.pickle in a write byte mode, and I'll name this file as model file. Okay. Now I'll dump my object, the model that we created in this file, and we'll close this file. And always remember that you close this file. Okay. I'll just execute this. As you can see, a model file I have created few seconds ago. Now let's test how our model works with a pickle. And now we have converted our model into pickle, but how will we convert back into our models? So what this code makes sure that whatever model file I have created, it opens it and stores it in a variable called as model. So model can be used in a similar way as a regular model, and I'll test this, okay, with first 50 data points. Let's see confusion matrix, and it is pretty good. So we have made this model just to expose it on a backend. Yes, we can always do better than this, but our objective was completed of model building. I know the video became a bit lengthy and I hope you liked the video. Please subscribe to this channel and I'll see you all in the next video. Till then, bye bye.